So when I do that, I get the following: 1 over phi of phi, and then my second derivative in phi. And then I get a plus sine theta over the function theta times derivative theta of sine of theta times the derivative in the big function theta with respect to theta, and then plus 2ie over h bar squared times sine squared of theta equals 0. Oh my goodness. Okay, so now we are finally in a position where we can separate. And we're going to separate the phi's and the thetas. I promise you this is going somewhere logical. So when I separate the thetas, I get 1 over. Oops, that's supposed to be a theta. Okay. So I get that, and then of course this second derivative of that function phi. And so all of these terms correspond to the sine, okay? And I can even separate out that sine of theta because this function doesn't have any of those dependencies, and I can separate them back out because I'm going to multiply them back together, okay? So then that becomes plus 2ie over h bar squared all equals 0. And I'll remind you, we've already solved this thing, okay? So look, I've got that phi function right there. I'm going to keep this going with the algebra, and I'm going to rewrite this as the following. So I'm multiplying through this phi over here, right? And so now this becomes second derivative of this function phi plus 2ie over h bar squared times phi equals 0. We've already solved this. We have already solved this function. I'll show you. It's back in the particle on the ring model. Look, there it is. I think I just passed it. Yes, look at this, right? Second derivative of phi of some function psi plus 2ie over h bar squared times psi equals 0. Okay, we've already done that. Brilliant. So we have a solution for this already. That's fantastic. We know that, of course, ml equals the square root of all of those constants, 2ie over h bar squared. We also know that this wave function, which we're now calling phi, right, will equal e to the I ml phi, where that ml takes on the plus minus values. And of course, this has to be normalized, and we normalized it already. Fantastic. So when we go to separate the phi dimensions, I'll just write all of that out. Sine of theta over the function theta times dd theta of sine of theta times dd theta of the function theta plus, and so I'm going to write all of this, this 2ie, that's still there, because we have to keep it attached to the sine squared, okay? And then also what happens is, oh my gosh, I'm failing at what I did here. Well, I'll write down what I have in my notes. I've got a 2ie over h bar squared times sine squared of theta equals all of these constants, 2ie over h bar squared, all squared. And why did I do all that? I think I did that to factor out that sine squared of theta from this phi. But it doesn't matter. And the reason why it doesn't matter is because our guess for this theta function is really difficult. We're not going to do it. So solving this equation becomes well out of the scope of the class. I've already been flubbing around with this math for the last 10 minutes. I would have to flub around with this math for a couple of more days, or have you take partial differential equations. So we're not going to do it. We're not going to worry about solving it. But the important thing to note is our phi still has this e to the IML phi dependence, okay? And so when we go to guess for theta, and then we plug our guess solutions back into this equation, right? When we recombine those results, so we put this EIML phi back into here, and whatever crazy guess we've come up with theta, we put back into here, we get a very special result, okay? And that special result is what we call the spherical harmonics, all right? So in other words, this theta of theta times phi of phi equals my original wave function, okay? And then when I go to normalize that wave function, so this is why I didn't normalize this phi result, because we have to normalize these two results together. So when you go to normalize this wave function with theta and phi dependencies, we get a very special function called the YLMLs, which we call the spherical harmonics. And what's special about these spherical harmonics is we get a new quantum number L that arises from trying to solve this system of equations. So I'm not going to hold you responsible for continuing through this solution. So we got a pretty good way through it, applying the separation of variables trick. But effectively, what we get, the normalized wave function of theta and phi becomes this YLML function, okay?